So I thought that was important. I thought it was worth spending some class time. I chose this class because you guys are closer to transferring and moving on. So I want to make sure that you're aware of all the resources that we have on this campus so you can take advantage of them, because they're important, especially to get into the schools that you want, right? And you're not limited to CSUN or other Cal States. You're not limited to UCs or California as well. Choose what you want, apply to what you think you could be competitive to. They'll help you become more competitive with your application process, including writing letters of rec and stuff like that. And then at that point, whatever you get accepted to, then you could make that decision. But there's no reason not to apply to things until you've got, I've told this to many students that were capable of getting into Harvard. Apply to Harvard if you really want to. At the very least, you get a letter saying you got rejected. That's kind of cool on its own with their letterhead, right? And it didn't cost that much to get that, and they officially sent something back to you. So, depending on where you're at in your process, don't be shy to try different things. If you don't get in, so what? Right? It doesn't hurt. But if you do, and you're pleasantly surprised, and then you decide later you don't want to go, that's okay too, right? It's your decision once you've put yourself out there and given other people a chance to evaluate you and then make that decision. So you're not limited to anything, right? And I've seen, we have, I think I've mentioned this in this class before, but Cindy Barrios is graduating next week from Berkeley. She's having the ceremony. She was here sitting in the same, in fact, I think she took my Chem 51 initially. And then took the challenge exam, got into 101, 102, and then transferred. She's, I think, environmental science major over at Berkeley, right? So just so you know. And then she's now doing research. She's one of 5 UC students picked to be in a special research program, and she's going to finish that off this year, and then I think she's going to apply to PhD programs, just to put that in perspective. So you guys are all capable. Just you're not limited either. And don't worry about finances. You can get financial aid depending on what you've gotten here when you get there. And if you do a good job and work hard, you'll be able to pay it back. Right. That much I can assure you. Okay, getting to the lecture so that you guys can transfer. We've got some business to take care of before that. Where were we? We left off what I called.
We just finished titrations.
We finished titrations. Did we get into KSBs? We did, right?
Yeah.
Okay, so we talked a little about molar, I think I brought up the idea of molar solubility versus KSB.
That's where we start. I stopped.
Okay. I think we saw here that you would expect KSBs, as they increase, so would the molar solubility, but they don't actually always work that way, primarily. And you guys, I guess, have had this in lab, if I understand it right. But when you have something that dissociates, you're looking at the moles of that place. So here you get 2 moles of hydroxide, and that, unless you're identifying the same types of things where you're getting the same moles, they don't always correspond the same way in terms of the KSB and the molar solubility. The KSB is simply the equilibrium constant for something that is a solid that will break up at some level into ions. Okay, that's the molar S. That's the KSB, the solubility product constant. The molar solubility is taking a certain amount of moles, putting it into a certain volume, I think they set it at 1 liter, and then whatever you could put in there until it saturates and comes out of solution. Okay, that term saturation. I don't know how familiar you are from Chem 65 or the equivalent, but if you take anything and you saturate the volume of it, if you're putting a solid in a liquid, then what happens? It comes out of solution. So then that's what the molar solubility is. At that level, right where you're at the cusp of saturating something, that's your molar solubility of any particular substance or compound. So those are the distinctions between these two things. However, you can find the molar solubility if you have the KSB and you use stoichiometry, the same way we've used it up to this point. So when you take something like a precipitate that you learned in the double replacement reactions from Chem 101 and, just 102. So I mentioned Chem 65, I meant 101 and its equivalent on the solubility. But when you get a precipitate off a double replacement reaction, also called aqueous reactions, the assumption there, and you guys see this in the lab when you did the experiment, the double replacement experiment, is you form sort of like a cloud. Right? And that's a solid formation. That's one thing that originally was not connected to something else, put in together, and then together they came out of that solution and formed a cloud. We call that a precipitation reaction, and that was the reaction itself. That implied at that point that, let's say, all of that precipitate, everything in there in that stoichiometric ratio came out as a precipitate. Once it's a precipitate, some of it forms an equilibrium and redissolves. And they go back and forth into that dynamic equilibrium again.
That's not good.
But a very small amount. So the solubility, the molar solubility is the amount that I could put in before it comes out. The KSB is if I look at that precipitate now coming out and forming ions and that equilibrium going back and forth, that's the KSB, right? So the KSB is only going to have the product in it, not the actual reactant, which is now the solid, right? Because remember, we don't include solids in the equilibrium constants, right? So the idea there is that should these numbers for KSB be really high or really low? If you understood everything that I just said, then this should put it in perspective. They should be what? Low. Really low. Because you form the precipitate. Now you're looking at the precipitate and you're saying some of it's going into its ions.
Yeah.
So there should be very little going into the ions.
Mm-hmm.
So the KSB should be very low because your product is above the reactant in terms of concentration, and that means your numbers primarily are fairly low for the KSBs. And that's essentially what you see here, very low numbers. Okay? But that's the idea. We have to account for it. But in that accounting for it, then you could presume that the solubilities are going to be also relatively low. We're going to then look at the formation of things as well in this chapter, and hopefully today, if I can get through this fast enough. And in that, you would expect the solubilities, the KSBs, I should say, or in that case, the K of formation to be very high. So I just want to put that out there now. We haven't discussed the formation yet, and I'll get to it. But I want you to start thinking about that now, as the KSB, the breaking up of that into ions, is going to be very, very low.
Would the K of formation be like the reverse of KSB?
Not quite, but you'll see. You'll form something, it's the formation of something, so yes, but it's the formation not of this, of something else. And we'll get to that. But I just want you to have that sense of if you're forming something, generally that formation is going to have a high K, an equilibrium constant. Whereas if you're dissociating something that formed, the presumption would be that it would be a very low K. And then the K type is just whatever it is that you're referencing. In this case, we're referencing the solubility product, therefore KSB, in the breakdown. And that should be very low, keeping that in perspective. Okay. Okay. KSB is smaller KSB, but higher solubility. And that's just because of the stoichiometric ratio. Oh, this thing works? Okay. So I just fiddle around and eventually it does what I want at some level.
Professor?
Yeah?
So let's say, you said if you're dissociating something forms, so you're saying
No, if I'm dissociating something versus forming something.
Oh.
Two different things.
So if you're dissociating, let's say you're taking a solid, right, and it dissociates into ions, so you have more of the products.
No, less. Your presumption is that the thing that you have made is not going to dissociate a lot. So in the past, in 101, there was no dissociation. It was just it formed the precipitate. Now we're saying once it forms a precipitate, some of it will go back into forming ions, but a very small amount.
Very low.
Yes, yes, that's what I'm getting at.
We see that little cloud.
What's that?
And that's why the KSP
Is low. That is the KSB. That is the equilibrium constant for that dissociation. In this context of taking a solid, breaking it down to ions, we're calling it KSB. It's just a constant. We're adding the SB as solubility product. The solubility of the solid. And, good luck.
Oh no, I was just saying, like, if you add a little bit more than of that solution that is making it solid, then it's going to actually go ahead and precipitate it right away.
So if we look here, just to put this in perspective, what I'm really saying here is this is the compound, let's say MgOH.
Right.
That's a solid, right? Let's say a solid. That is going to form an equilibrium where I'm going to get Mg2 plus ions plus 2 hydroxide ions. That's all I'm saying.
Okay.
And that the formation of these are going to be very small relative to what you have here. Hence the KSB, which is these on top. This isn't included because it's the constant on its own. This on top is going to be very small, and that's the KSB value.
Okay.
That's the solubility product that I'm referencing. Okay. The molar solubility will be the molar solubility of this thing, which then therefore would be similar to these in terms of, if I formed an ice chart, what would happen here? I start with this and I get this. So this would be plus x plus 2x.
Right.
And this would be what?
0.
0, but it also can be labeled as what?
Something
Minus x.
Yeah.
In other words, the x lost here, or gained here, is the x lost here, which is going to be very small or insignificant relative to the concentration of it.
Right.
Right? So because there's such a small amount, but there is some amount reforming here, and I gotta account for that. Now, going to your question, if I have more of one or the other, what will happen to this?
Oh, shift.
Will shift, Le
Right.
Chatelier's principle, and that should account for what I think you were mentioning.
Yeah.
Right? So if I add, in other words, if I put, this is presumably in water, right?
Right.
Big thing that we're gonna talk about, I think, a little bit later here. But if I put this into a basic solution, what would happen? It's
Oh,
gonna
okay.
shift even more this way.
Right.
Right, absolutely, because the hydroxide
Okay.
here is gonna shift it this way. Yes. So under different conditions, different things will happen. Okay. Okay, so let's do an example, and we'll go with that, and we'll see where we're at from there. So the solubility product, this should be really, really simple. What would be, oh, I actually just had it on the board, I guess. This is the same kind of thing, right? So it'd be this. And the solubility product would be the KSB.
Concentration for magnesium times concentration for
Squared down.
Right? Nothing new there. That should be very straightforward for you. What's new here is that this will actually happen. Where in the past you didn't know that this would actually go into that. And now we're presuming that not everything is going 100% one way or another. That's all I'm really saying, right? Okay. Oh, we're gonna do, okay, so let's make this a little bit, you're just dealing with the 3 and the 2 there, right?
Yeah.
Okay, so I'm going to move through that relatively quickly. I'm going to spend more time explaining the concepts so you have a sense of what's going on, and then the things like this, I'm going to move through relatively quickly because this is stuff you already know.
There's one more of these. And then another example
Wow,
was different.
okay. So same thing, just 2 was that. Dan, where's that 2 coming from here, separated? No big deal there? Good. Okay. Oh, so now they're going to go back and define molar solubility. Okay. So it's the number of moles in a compound that dissolve in 1 liter of water to give a saturated solution.
There's actually one example in here that wasn't on the PowerPoint. I wasn't sure how to solve it. It asks which is the greater solubility, barium fluoride or calcium fluoride. And that's all the information it gives. I don't know. And I wouldn't
I wonder
really
if
know
it's
how
a
to.
KSP, right?
Did you just look them up?
And it has your chart here.
Oh, you have a chart on your phone? Yeah, okay. Yeah, I think we're going to get a chart here too. So we'll take a look at that. Okay. Okay, so solubility of silver chromate in water. Okay. I know I've made this point. I'm going to make it again, and I'm going to, because I think it's a really important point. All the things we've done up to now, the presumption is this is all in water. If I put this stuff in something else, it's not going to have all the same numbers and the same types of reactions that you are used to, right? And you should really understand that now, because if I put something in an acidic solution or a basic solution, I think we did that at the end of oxidation reduction, so it was in the thermodynamics section in Chem 101 or something like that, where you did half reactions of redox reactions in acidic and in basic conditions. Is that not true? Didn't you do that in Chem 101? I think so. And so in there you got a chance to see that when you balance those equations, they're different because different things are involved. It's not just placed in water, right? And then we've done some things along the way where I've said, okay, make sure you understand the equation you're looking at prior to trying to solve the problem so you know what's happening in it. And then we'd have one equation, and then if we added something to it, like with buffers, that created the second equation, and what happens as a result of that. So in a way there, we were doing that, even though the foundation of everything was in water. Okay. Once again, we're still in water, and it's emphasized here. But having said that, it doesn't have to be in water. I could put it in a variety of things. And then all of this stuff is going to change in how you evaluate it. Okay, and I think this chapter should talk a little bit more about that as we come up. Okay, so what do I have here? I have the silver chromate in water, and its solubility is 0.022 grams per liter, and calculate its KSB for the silver chromate. The first thing I'm going to say is, if I'm looking at solubility, how did I describe it for this molar? So then what do I need to do here? I convert the grams to moles using the molar mass of the silver chromate. That should be an automatic. And why is it in, so just intuitively, why do we care about molar solubility here? As opposed to why not just leave it in mass per volume?
The molarity?
Molarity, and why do we care about molarity?
Also the leading?
Your equilibrium constants are based on molarity. They're based on a concentration, and this is still a concentration. Let me remind you of that, right? However, we've been dealing with molarity because of the molar ratio, because of the balanced chemical equation. Therefore, the molar concentration is much more important.
Right.
Okay, just to keep those. Okay, so the KSB. So first, we're going to calculate the molar solubility. Then we're going to set up the solubility equilibrium chart, and then we're going to calculate KSB. Okay. What's my equation here, just to make sure we're clear?
G2CRO goes to separate
Silver chromate goes to, in an equilibrium, what?
silver and chromate.
2 silver ions and 1 chromate ion. Okay, just make sure the terminology is clear. Okay, so this should be, here we're just converting, we're using the molar mass. So we'll say the molar mass is 322, that's the silver chromate, grams per mole, and there's my molarity. Okay, well, my molarity of what was given here, what did we find here?
Silver chromate
The molarity of silver chromate when
in water.
it's in water,
Was in 1 liter of
Yeah.
water to give a saturated solution.
so that's right. That's how much I need. I can put into 1 liter of water to get a saturated solution.
Okay.
Okay. So that's solubility, so we already did this here. Now, this starts at some amount, right? But we don't care about it right now. This is 0 and 0, assuming that we started, everything went to a solid, or we started with the solid and we put it in water.
Right.
Either way. Now, minus x plus 2x plus x changes 2x, change x. Here I don't have anything. Why?
It's not part of the KSB.
It's right. It's a solid. It's not part of anything. Why is it not in the K?
not
It's
in
a
the-
solid meaning, no. But what was the rationale for that? Right? It doesn't change.
Right.
Right? Pressure, volume, nothing changes there.
It's not going in the equilibrium. Yeah.
So it's a constant, basically.
Mhm.
As a constant, isn't that what K is, a constant?
Yeah.
So you just incorporate it into that constant. And so now it's part of the constant, okay. But why did I put the negative x there?
So you can keep it straight that you're losing something.
That I'm losing something. Now, you could assume that I'm clearly not going to lose that much, so this really won't change.
Right.
But it just it keeps me aware, because now if I have x here, then I have a sense of what's happening, what was lost from that silver chromate, even though it won't be significant relative to the starting amount. Okay. So here's a 2, hopefully. This we didn't explore that much up to this point in all of our equilibrium constants, right? We've had quite a few up there. Okay, KSB, so this is just 2x squared times x, right? What we get? It's our KSB right here. So that's 4x to the third. Okay, and the KSB was. Okay. This thing does not want us to operate. I can go forward, but I can't go backwards. Okay. So, what was that number again?
6.63 times 10 to the negative 5.
Was that our KSB or was that our molar solubility?
Molar solubility.
Molar solubility. So what is that?
That's going to be
The
divided.
amount of moles per liter filled dissolved or saturated.
That's what I'm basically starting with here, essentially, right?
So
Or
we should add it in there.
is that X? That's X.
Is the X, yeah? Minus
because
the-
that's how much is soluble,
Oh,
right?
the remaining stage, yeah.
Right.
Mhm.
So that becomes the molar solubility in this case is X, and that's that number we got there. And if I now put that in, right, the KSB is what? Just 4 times 6.63 times 10 to the minus 5 cubed. Everybody know how to do that on
So
the
even
calculator, by
smaller.
the way? Make sure that you're
Yeah.
familiar with that.
That's even smaller.
Right, it's gonna be a lot smaller. The KSB is gonna be 1.2 times 10 to the minus 12. Is that what we'd expect? Would you expect it to be very small?
Yeah.
Yes, and it is. So the key there was what? What am I trying to point out here as the key in solving this?
The molar
The, what the molar solubility means. And how it fits within the context of the KSB. Okay? Because I could also give you, and we will do things where I give you the concentration, say, of these, or this, or that, or both, or whatever, or the KSB, and I could ask you to solve for the molar solubility. But in this case, I gave you the molar solubility, or you solve for it because it was given, then you just solve with the molar mass, right? So everybody recognize what you're getting, what you could get. So even though we do this problem here on an exam, I could give you something else. I could say, here's the KSB, what is the molar solubility, for example, right? In that case, I have this, I don't have the x's there, and I solve for x, right? So it's, right, I just want to make sure that that's clear, that it doesn't always have to be this way. And if, depending on how you see it, will depend on how you solve for it. Here, this is it right here. Same kind of thing. So what is the molar solubility of magnesium fluoride in water? What's the first thing? What is your equation? MgF2 as a solid. Equilibrium goes to Mg2 plus 2F minus. Okay, so that part should be pretty straightforward. Once again, is this a different type of equation than what you've used? Yes. So you got to be able to juxtapose which equation, what am I looking at, why am I looking at it, how do I relate it? So there's the minus x of this, plus x, plus 2x. So x is the molar solubility of MgF2, obviously, here. And I get this, I plug in my KSB, basically the same thing there, and I solve for x. And that's my molar solubility.
Could you go back a couple slides? I
Yes.
just want to make sure, because there's something on the page here that doesn't quite make sense.
This?
So keep going back one,
Back?
to the actual ice chart.
This?
Yeah, so on our page, they actually have for the chains, they just have a dotted line coming through instead of negative X.
Oh, here?
Yeah.
Yeah, right. That's what I was pointing out why I put this here, right? I put this here so you can see what is this number representing?
Okay.
It's representing the molar solubility, but it's, let me do this.
Oh, that's the second.
The amount of this versus this, is it significant? No, not even close. So you could easily put a line there.
Okay.
I only put the negative x to express that this is what we're solving for. And why does that matter? Because then solving for x here, it's not the 2x, it's just x. Right? That's important. So if I had a different ratio on here in terms of the molar ratio, if this was 2, then I'd be solving for 2 of them. Right? So I'm solving for x here. All it's telling me is that is my molar solubility. And if I solve for x through this process, I now know it. This should be a line there, because really there's nothing going on, which is exactly why there's the dots here and the dotted line here.
Will it ever play any effect? Or
Well, what?
will it ever play any effect?
No, why? Because it's a solid. Right? So it's not really changing enough to matter. Right? It's a constant, essentially. So as a constant, it's already part of the K. Remember that from like the first chapter, first equilibrium chapter we covered, which was probably the second chapter after kinetics. So anything that's a solid is already part of, because it's not changing, it's already a constant and it's incorporated into the equilibrium constant.
In water.
Right. Okay. So, but I just put it there to emphasize what's actually happening and what you're solving for in terms of x. Okay. So that's the same thing here. It doesn't have to be there. Okay. So now KSB is just this, blah, 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 and I get this. And it's very small. Oh no, that's my KSB, so then I solve for X, my molar solubility, and that's a little bit larger than that. But still very small overall. 2.6 times 10 to the minus 4. It's okay? Any questions? Procedures are all pretty much the same here, just the intellectual concept about what's happening has changed just a little bit. We've just added something, that's all. Okay, so solubility in the context of the common ion effect, and this will be pretty simple for you. So if I'm looking at the solubility of calcium fluoride in a solution that has 0.1 molar sodium fluoride in it, what's going to happen? Is the solubility of the calcium fluoride going to increase or decrease, and why? Decrease because
You're adding more of the fluoride.
you're adding more of something that's going to, this is, by the way, what is this? Is this an ionic compound? Ionic compound
Yeah.
that's not going to separate. Why do we know that? The sodium never
Soluble.
is always soluble on the solubility chart, sodium, potassium, ammonium, remember
Right.
that? So we know this is going to separate completely, forming fluoride ions.
Right.
The fluoride ions now will influence the calcium fluoride forming ions by shifting it back towards
To the left.
the calcium fluoride,
Right.
right?
Shot.
Okay. So here's this here. I'm adding the common ion here, which is going to shift this way, right? And that would decrease the solubility, just as you guys pointed out. Once again, that should be a pretty straightforward concept based on what you guys already know.
Yeah.
Okay. In which solution, okay. How many of these I don't want to give, hopefully there's.
There's only three.
Okay. If I give out one more, it might tell us, right? In which solution is barium sulfate most soluble? So if I put it in barium nitrate? No. By the way, nitrates are going to, they're soluble, so this is just going to form all ions in solution. Sodium sulfate? Same thing, I'm going to form all ions. So in this case, I'm going to have barium ions influencing this thing from dissociating. In here, I'm going to have sulfate ions influencing this from dissociating. And sodium nitrate, what about that?
Oh, really?
It's not going to do anything, right? Presumably? Okay. So this won't, so then what's our answer here? Okay. Hopefully that's obvious. That's a great test question, right? Because it's so easy. Anybody unclear on that? Just looking at that little concept we just looked at on whether or not you have a common ion, and if you do, that common ion effect will shift it back towards the solid, which then would give you a lower solubility. Okay, what is the molar solubility of calcium fluoride in a solution containing? Okay, so now let's figure out what the new molar solubility is. So you could figure out what the solubility, the molar solubility of calcium fluoride in water is. Now what if I put it with the common ion? Right? So how's this going to be different in terms of your ice chart?
It's
Yeah,
actually,
you're going to have a different starting value of the fluoride ion, absolutely. Okay, so this is the equation. This is all separated, so it's going to influence this side over here, right? So that's right there, the 0.1 molar, because, okay. Common mistake. Let's say I had, that is calcium. Let me make this into, I'm going to make it into something, and I'm going to assume that it's going to be soluble, 100% soluble. So let's say I put BEF2. So in this case, saying this is a solid. So most likely most group 2 cations are going to be insoluble with fluorine. Let's assume beryllium is not insoluble,
Okay.
right? Or is insoluble, not soluble. So that means this will go all the way to Be2 plus 2F minus, right? If this is 0.100 molar, what is this one?
0.1. Yeah,
0.2.
times 2, yeah.
I just want to point out why I'm saying this. Here, the sodium fluoride, you're assuming is separating completely. It's a 1-to-1. So that's why the 0.1 is 0.1 and why you can put that there.
Yeah.
Okay, is that clear?
Mhm.
If this was something where it itself was in an equilibrium, I'd have to find out how many ions I have of it. And if it was in a different ratio, that even if it all separated, then it's 2 times the 0.1. Okay, just to make that really, really clear. I know that's a point where people have gotten confused in the past. I maybe give an exam where your assumption here is that, you know, you see something like this, but now you have 2F2 there with whatever it's connected to, and like, for example, zinc or something like that, right? And now all of a sudden, you just copy what you did here and you put 0.1 when it should be 0.2 to start. Because this is the number of ions in terms of the moles of that ion. Okay, and so I want to make that clear. So the molar ratio here, this is, and maybe I should write this up, this is going to be 2 times 0.1. Just to make sure everybody sees what I'm saying there, which would just be 0.2 moles. Okay, we're in the same volume, so that's the same thing as 0.2 molar. I think that's a question that Jenna asked a few days ago. Okay, the concentration versus the moles there. We're all in the same volume here. Right? Okay, is that clear, what I'm doing there? I want to make sure that that's a weird little sticking point sometimes. Okay, so that's why I'm starting with 0.1 here. This is presumed to be completely dissociated. I start with 0.1, I get one of those, I end up with 0.1. So now I go through the change. This is going to be what? Plus x,
Yeah.
plus x,
Yeah.
2x. 2x. You're using the new equation.
plus or minus?
Plus.
Oh, minus because it's shifting that way.
Well, yeah, you're adding more fluoride, so.
Plus 2x.
But you already
Plus
like-
x.
What's that called, the limiting?
But I thought the common ion effect was shifted the other way.
This is just what I'm starting with, and I'm looking, which is exactly why I asked you guys this. What am I doing here? I'm starting with this, and I'm looking at the dissociation of it.
Okay.
Okay? So the first thing I do is I say, how much of these things will I have?
It's formed.
Okay?
Let's see what you're saying.
So my KSB is this. My F minus is
I see what you're
this.
saying. Yeah, you're not.
This is from solution of the sodium fluoride.
Yeah.
And there's my KSB, and there's my X. So what happened here? What is all this mess?
That's your molarity, your molar solubility.
Okay, my fluorine is put in here,
Mm-hmm.
and I'm still stuck with X there for calcium, right?
Right.
I get this, and now I solve for X. What was X?
Your molar solubility.
Let's
Oh.
wait till, give me 1 second. What is X?
'The calcium.
And it's the molar solubility of what?
Of calcium.
Calcium
Oh,
fluoride.
Right.
This is the
Sodium fluoride.
in sodium
Oh,
fluoride.
okay. Yeah.
This is of calcium fluoride.
Right.
Okay. So X, what is this number here?
X is your calcium.
This is the solubility in pure water. What
Okay.
happened here? This is a whole bunch of stuff that I just moved you right through. What's going on? I want you guys to think about it. You tell me what's going on.
Smaller whenever
No, because bigger.
the common ion.
Is the solubility greater or less than in water and in sodium fluoride? Which one is the solubility greater in?
In water.
Water.
Because there's not
Bigger.
Because the common ion.
Because the common ion shifted it,
Right.
right? So now let's go back over how did we determine this? So this is from sodium fluoride, so maybe I should go back, huh? What's happening here? Did we have, what was example 1? No, that wasn't it.
Which pure water.
So I have a change here. I'm starting with this, and this is my change. right? And so I take the KSP backwards. So my change here is plus 2x and plus x. Because I'm going from here to here, that's what I'm evaluating. That's what KSB is, right? Can I go the opposite direction if it's KSP? Let me start with that, no. That's what KSB is, the solubility product. That's the first thing I'm gonna point out, right? So if I had this as just 0 in water, then this would be what, 2x plus x. Overall, I would get what?
Just
4x cubed equals, do I have the KSB here? Okay, so they didn't give us the KSB, but let's assume we know the KSB. You would get the KSB in any particular answer. So the KSB, we're gonna say is this, I guess, right? And this should match the KSB in your chart. So that should have been given in the problem. Okay, so let's start with that. So now, if I take this and I put it into that 0.1 molar, which allowed me to get the 0.1, this was only 1 here in our actual thing, so this would be 0.1. Then I could plug that directly in here. I get 0.1 squared times x, right? And since this is my KSB, I put that in, I solve for x, and what is x? My molar solubility. Okay? That's my molar solubility when I have it in sodium fluoride. Now, before we go, well, because I have 2 questions. Now, if I were just to say this is not here, what would this be? 2x. So the whole thing here would be 4x cubed. So this divided by 4, take the cube root, what do you get? This, right? And that's the distinction between the two. Now, question in the back I saw?
I'm already answered.
Okay, which is why I wanted you to wait, Jenna.
So for the ice chart, you wrote that the equilibrium for fluoride ion was 0.1 plus 2x. But then when you actually wrote out the solubility constant, or the
What happens to 2x?
What
It's so small.
Thank you.
It's new.
But then you're also worrying about, I guess, because 2x is larger than x for k.
But it's negligible. If, oh, watch.
Because if you
Watch,
times
watch,
it
watch,
by
watch.
some number, it means a lot, but if you add or subtract by some number, it's
So what is x here? This is x, right?
yeah.
0.1 minus that, what do you get? Put it in your calculator. What do you get? 0.1, right? Does that help? That shows how negligible it actually is, right?
Okay.
This doesn't even factor in even close because it's so small. So 0.1, now, oh, go ahead.
So when you're saying the solubility in sodium fluoride, it's the solubility of the whole ion?
Of the calcium fluoride.
Okay.
So that's the molar, so, okay. When I put a compound, no, this is important actually, what she's asking. When I take a compound and I put it in water or I develop it in water, I'm saying it's a solid. This is then saying that there's an equilibrium where some of it forms into ions. So what is the molar solubility of the compound? In other words, at what point in that volume of whatever I have, water in this case, or say in something else, below this point, what happens? If I have, let me rephrase this. What if I have less than this of the calcium fluoride to start? What does that mean? I like that actually.
Oh, it's completely solid now? It's completely
That means you
solid?
don't have a precipitate.
Right.
Yes. Does everybody recognize that? That's actually, I like how that came out. Because that's already implied in my head, but that's obviously not to everybody else. If I have under this amount of the calcium fluoride, I don't have any solid. Because the molar solubility, it's also, once I pass that point and go well past that, it's now coming out of solution like it's saturated in that volume. Right? Does that make sense?
Yeah.
So then what you're looking at, the molar solubility is of that solid. Or I should rephrase that and say the compound. Because if you have less than the molar solubility, it's not a solid, right? Peter?
The 0.100, the plus 2x, that 2x is negligible, right? So
Yes. Yes. Right? So, yeah. So that's okay. If you take 0.1 minus this, what do you get?
Basically 0.1.
0.1. Right. Hence, 2 times that. Does it change the 0.1, or take 0.1, I should say, plus 2 of that? Does it change the number? So 0.1. Plus, minus, whatever. Go ahead.
How did we get the solubility in water again?
You mean the KSB or the molar solubility?
The very last.
Oh, here?
No, the next one, which is the 4x cubed. The 4x
So
cubed.
this would have been, let's assume that we don't have any sodium fluoride in there, right? So then the ice chart would indicate this. So I have calcium fluoride, and I'm going something like this and this, right? And I'm getting Ca2 plus 2F minus. So here, when I have the sodium fluoride in there, I have 0.1. Without it, then it's just 0 and 0 to start. Okay? So that means the change is plus x and plus x,
Plus 2x.
right? And I'll go 2x there. So the KSB is going to equal x times 2x squared, which equals 4x cubed equals the KSB, and now you solve for x. And that gives you this number here. Is that okay?
Or it'll give you the next number, not that one.
Well, if you solve for x, you'll get, oh, I see what you're saying. Well, this is x here, right? So this
That's
is,
the.
oh,
that.
this number, you're
Yeah.
saying, yeah. So this is with the calcium fluoride in the sodium fluoride, where you're starting with 0.1 molar of the fluoride. This is the molar solubility of the calcium fluoride when you're starting in pure water without any of those extra fluoride minus ions. Does that kind of wrap it up a little bit for everybody? Hopefully.
So do they take that same KSB equation but put 1 point, the solubility of water on the other side of the equation and then get that answer for x? Is that how they get the solubility in pure water?
No, they just took like part 1, remember how they just used 0 for transition? That's what they did, and then they gave a equal to the KFC and just solved for x. So it's like a part instead of first example.
So the only difference is you're either starting with this in pure water or you're starting with this in the sodium fluoride.
There's no common.
There's either a common ion or not. Now, if I had something, these are where the difference, this is the difference between these two in how you say, everything else stays the same. So this becomes 2x squared, and this is just 0.1 squared. And that creates that difference in your molar solubility. And that's because of the common ion effect, where you're starting with a concentration of one of the ions, which is therefore shifting it back towards the reactant in this case. Okay. Well, we're moving much slower than I thought. Okay, so so let me take it back here. In this example here, if I put this into an acid or a base instead of water or sodium fluoride, would it make much difference?
Yes.
How?
Well, if you're
Let's start with an acid. I have extra H pluses. Would the H plus influence the F
Yes.
minus?
Yeah,
Yes, why?
it's gonna bind to,
It's gonna
It's a weak acid.
right.
Yeah.
So it's going to pull, the H plus would pull some of the F out,
Yeah.
which would then shift the equilibrium this way.
Right, to the right.
Okay. So if I do put these things into an acidic or basic solution, it will change how the solubility of the compound is, right? That's all the next part says. Except for they give you a much more clear example. That one's a better one because you would have to recognize that the H plus could bind to the F minus. Could the OH bind to the calcium as well?
Yes.
Okay, so you'd have to account for that, right? If I give you something more straightforward like this here, then the solubility of this is going to depend on the pH, right? If I add A low pH, meaning a more acidic, would that affect this? Yes, it's going to pull it out and shift it which way?
So, right,
To the right. What if I add base?
a lift.
It's going to shift it back to the left.
Take it back.
Everybody see that? Bless you. Everybody see that?
Yeah.
Okay, good. Okay, so, Peter?
Do we just use just look at the most allowed definition, not Lewis, or?
You mean, how are you defining whether or not something's an acid or a base?
Yeah.
And we're gonna talk a little, we're moving through that. In this case here, the way I just described it makes it more simple. But yes, if you have what's a Lewis acid and a Lewis base again? Donating of what? Electron pairs?
Takes pairs and then a base donates pairs.
So we're gonna see how that potentially has an effect on these things as well. Okay, so let's wait to get there. So in this case, we're just simply looking at adding a hydroxide or hydronium, which would be the Bronsted-Lowry description. So here, just like we talked about, we add a base, it shifts it to the left, we add an acid, and it shifts it to the right. No big deal, just Chatelier's principle and understanding that this will adjust the solubility of the compound when I have it in a solution other than water. We've seen it if I have a common ion effect in the solution, or if I have a difference in the pH from 7, which would be water, right? Then it will affect it depending on what it is that I'm separating. This is kind of just the same example I already gave you from when I went back to the calcium fluoride, right? This is the same concept here. So this would form, this is the conjugate base of a weak acid. So that means if I put in this into an acid solution, it would shift it this way, right? Same concept as the fluorine. And if I put a base in, if I put this under basic conditions, would it do anything? Depends if the calcium binds it or not, right? So is calcium hydroxide what is that? Is that a strong base, a weak base, whatever? And if it's a weak base, then it could have a varying effect and shift it the other way, and then you'd have a competition depending on which one was the weaker or stronger base acid combination.
So you're basically saying if you put that in water, then it's going to take the proton, and then the leftover hydroxide will bind with the calcium.
If I put this in water,
Yeah.
you're gonna have a molar solubility based on this, that's all I'm saying. If I put it into an acid solution, then this will be able to attach that H and shift it this way, because you'll pull this out of the equilibrium, which would then shift it towards that direction. Right? You will have a little bit come off, but you have so little coming off anyways. You don't have enough of this to start pulling it off the H2O to make it significant, essentially. But if I put it in an acidic solution, now I have a whole bunch of those, and that's going to cause that to pull off those H's since they're so readily available. Okay. So I form this. Right? I take this, binds to the acid, and I get this. So I'm shifting this away towards here, which then would shift this more towards that direction. Okay. Q, I think, Hurdley, you brought up Q within the last couple lectures.
We had a lab
What is
that
Q?
used it.
It's around there. It's just a comparative value.
Absolutely. Whatever concentrations I have, right, will allow me to figure out a number. If that number is equal to the K, then I'm at equilibrium. If that number is greater than K or less than K, then I'm at some position relative to that equilibrium. I just call that number Q. I think it was called the quotient. You could say Z,
Quotient.
whatever. It really makes no difference, right? It's just a number that allows you to identify where you're at relative to the equilibrium. Does that make sense? Okay. So we're going to apply that again in here to determine we look at precipitations of ions of slightly soluble salts and how they interact with each other. And we're just going to apply Q to see what happens. Are we at precipitate? Are we at molar concentration, molar solubility, or whatever else? Okay. So we'll go back to this example here. When I think of Q, I'm just thinking of K, just not at K. Right? I want to make that clear. It's not like it's a new equation. It's the same equation as K, but it's not necessarily K unless that number equals K.
Mm-hmm.
Then it's K. Otherwise, that number is going to be greater or less than K, which means that you're on one side or the other side of the equilibrium, and it will shift accordingly depending on which side you're at. That's all. Q just gives you a sense of where you're at those concentrations at that moment. Same thing. Same thing as K. Just want to make that clear.
Q would increase or decrease depending on how much of the solution you're adding, right?
What's that?
How much of the solution you're adding to make it into the equilibrium? 'Cause in
So
the
if I'm at some point
Mhm.
where I have Q and it's less than KSB, what does that mean?
It's- right, it's more aqueous,
Unsaturated.
right,
That means I don't have any precipitate left. The same thing we mentioned earlier,
right,
right? Just means I'm below the molar solubility, essentially, right?
right.
If QSB is greater than K, solution is
Saturated.
supersaturated,
Yeah.
Precipitate.
right? What does supersaturated mean? Maybe I should.
What is solid form? Solid form?
Past the saturation point,
Mhm.
and how would I do that?
Add more of the,
If I add more,
Add too much of the solid for the solution.
can I? Okay.
Oh, you can heat it.
I could either start it off really hot and let it cool, maybe potentially slowly down. Generally, when I put something in a volume and I have the molar solubility, will that change with temperature?
Yes.
I keep the same volume and I increase the temperature. Do I increase the molar solubility?
yeah,
Most things, yes, right?
Generally speaking.
Right. Now, then what if I let it cool slightly down, back towards room temperature?
right.
So I've saturated it at a higher temperature, I cooled it down to room temperature, supersaturated. I have something that now is, right, you see that, it's dissolved, but it's not completely come out of solution like it should, right? So you could think of these things in multiple ways, and I want you to have that idea that you're talking about volume of something inside that volume of something, and the temperature. These are the things that play a big role in what's happening when you talk about saturation, okay? Now, this is just saying solution is supersaturated under most circumstances, excess solid precipitates out of solution. But if I change those conditions and I heat it up and then I slowly let it cool down, I could have a whole bunch of stuff that's not precipitated that should be at that temperature, right? So there are a couple of things that you can do to make adjustments, but for the most part, this is how we're going to follow it. Solution is saturated right at this line. I like to think of this like this. I like the old solubility charts. And you have something like this. You have something like 100 grams per of water per mil or something like that. And then you have temperature. And the temperature goes up this way. So this may be 10 degrees, say this is 50 degrees, etc. And then I have, this starts at some point. So if I put, let's say, calcium fluoride into 100 grams of water, that's all that means, which is really just 100 mils, right? Then if let's say this is, I could say this goes, if I have something like here, we'll do something like this. Anything from this point down, this is essentially your QSP less than KSP,
Right.
right? At this point here, this is your equilibrium.
Mhm.
And anything above it is your saturated. Okay? So when you think of it in that context, it makes it a little easier to visualize what's happening here. You're shifting from QSP, which is essentially just going you're shifting from here to here, up here, over here. That's all. So you still have this amount here is what you have in this equilibrium. And then you just have a whole bunch of this usually, and that's where you get up here, it just keeps going up. That make sense? What's happening from a intellectual perspective. So that's all these Q's versus the K's are. Okay, so let's try. If I have lead 2 nitrate, I mix it with sodium bromide, and I get lead nitrate. Hold on, Jenna, before you go.
I just have a school event that I have to go be at.
Talk to somebody, because I'm going to discuss the exam
I'm recording
at
it.
the end.
Okay.
I wanted to see where I got to before I started that, so talk to somebody.
Okay,
I'm recording it.
sorry.
Oh, good, okay.
Thank you,
Yeah.
sorry.
So I have the lead 2 nitrate, I'm mixing it with sodium bromide, and then I end up with lead nitrate, lead 2 nitrate at 0.015 molar, and sodium bromide. So what is this essentially? What kind of reaction? It's a double replacement, right?
Yeah, double.
And
I take these, I switch partners, I get sodium nitrate
Yeah, and lead bromide.
and lead bromide, right? So if I mix them. Okay. And so a precipitate will form in the mixture, and that precipitate is the lead 2 bromide, and it's got a KSB of 4.67 times 10 to the minus 6. Okay? So the question is, will a precipitate form?
Oh, like, will it be
The Q, yeah.
saturated or-
Q and compare it to the KSP.
Yes. Will it be saturated or unsaturated?
Got it.
I'm going to determine Q here. Right?
Mhm.
Okay. So the first thing I do is I look at this here. And what am I doing? I'm taking this, and I'm binding to that, and I'm forming this. That's my double replacement. I just put it into the net ionic equation, essentially. Right?
Mhm.
No big deal? You guys can manipulate that in your head at this point?
Yeah.
Okay. Then, of course, I look for my, okay. What is my concentration of lead ions here?
0.150.
Yeah.
0.0150, yeah.
Okay, what is my concentration of bromide ions?
0.075
Okay.
times 2.
Yeah, squared.
So you guys told me this, right?
Mm-hmm.
You guys okay with this so far? I just didn't put it into the ice chart, right?
Yeah.
Make sure, okay. And then I just solve for the QSP. And I compare it. Is it less than or greater than this?
Less than.
Less than.
Yeah.
So what does that mean?
So no precipitate.
The solution is
Solution is what?
unsaturated.
Exactly.
Unsaturated.
Unsaturated, yeah.
So there's no precipitate found.
No precipitate will occur. Which should correlate what you guys are pretty much doing in lab right now,
Yeah,
We just finished it.
right?
yeah.
Well,
That was the
we're
last lab.
turned in the lab.
Yeah,
So it's in a different context, but this is the initial part of that process.
right.
What am I doing here? I'm taking an actual chemical reaction, as you guys are familiar with it, and I'm putting it into the double replacement, so I have to know that. I'm correlating the concentrations to the ions formed, and then I'm solving for what I'm calling Q, and evaluating where that is relative to what was given K. And then I'm saying I'm below saturation, I'm at saturation, or I'm above saturation. I've already saturated my system. Okay? What you guys are doing is more like a qualitative analysis where different KSBs, meaning different amounts of things, are saturated at different amounts, literally, right? So if I take different cations and each one I bind to something, so I could put that something in, I could precipitate one thing out long before another thing will precipitate out, right? And I could even potentially see different colors associated with that. And that's what qualitative analysis is. That's what you guys are actually doing in, I think, your 3-day experiment.
Yeah.
right? So this is just initially, let's see, can we determine if something is or isn't saturated based on how much we put in there? Then we'll be able to look at a bunch of things, evaluate them accordingly, and see how to saturate out using a certain amount of something without saturating something else out. Generally, you're going to spin it down in a centrifuge, which means you'll clump the solid at the bottom, you'll decant whatever you have left in your solution, which are things that have not come out, and now you've just separated the ions you have left with the ion that precipitated. And that's all you're doing in the quality analysis, right? Okay, so that's where we're at here in the lecture,
And that's where
which
we're
is
at.
starting to correlate now with where you're at, because you have a 3-day experiment. Now,
Yeah.
Yeah,
okay, what does this goes to the 30 mark?
25.
25, okay, let me see how much I get through here, and then we'll stop and we'll talk about exams. Okay. Okay. In example 1, what is the minimum concentration of the sodium bromide that will precipitate the lead 2 bromide? What do I do here? Set it equal to KSB, right?
Right.
Okay, perfect. So we have this here, we go through our KSB, so we have this thing is equal to the KSB.
Bless you.
So the KSB has to be given, by the way. It was given in the last one, right? So we just took, so even though it's not in this question, you could presume that it's the same from question 1, just to make that clear, if somebody can't find that. And so now the question is specifically, what is the minimum concentration of the sodium bromide that will be precipitated, right? So why do I have something here for the lead?
Because you're keeping the same concentration of lead.
Because I haven't changed the concentration of the lead 2 nitrate. Does that make sense, Arash?
Should there be a 2 next to the DR inside of the brackets, because you don't know?
But it's just the concentration. 2xx, it's just the concentration we're solving for, right? So that's okay. But yeah, right.
Yeah.
But if it's all x, then you would have to, because you don't actually know what that is.
Right.
Okay. So here, what it's asking is, what is the minimum concentration of the sodium bromide? Why is this kind of an odd question? Because if it was a good question, it would specify, based on this amount of barium nitrate, barium 2, or
okay.
lead 2 nitrate. Do you see what I'm saying?
Yeah.
Yeah.
So that would make this a better question. Is if I said, what is the minimum concentration of sodium bromide that will precipitate lead 2 bromide if I started with this amount of lead 2 bromide, which is what this amount here is, which is only the amount you had in example 1.
Yeah.
Does that make sense?
Which is the molar solubility.
Which is right.
Right.
So I could have used any number here. It's just how much bromide do I need to get this precipitate to come out based on the amount that I started with the lead. That's all I want to point out there. And that would be, just so you're clear, here's the amount of lead. That's where the 0.015 comes from. That was already given in the last one. Okay. So those would be the only 2 points of confusion really here. That's where this number comes from, and then the KSB is from the previous. So now it's easy, right? So now I just simply take this, I divide by that, I square root it, and that's my concentration of bromide. Fine. And that tells me that 0.0176 molar of sodium bromide, then I would precipitate out lead 2 bromide from this amount of lead 2 nitrate. Oops. Is that okay? Everybody understand that? Okay. These small subtleties that I'm pointing out, these are where you're doing it on your own, you get stuck. So hopefully you're like, otherwise it doesn't make sense for me to be up here if I'm not pointing out what's might be challenging for you. Okay. So here, I'm looking at the same kind of thing. So I'm taking 2 things, I'm bringing them together, and I'm predicting whether or not lead 2 chloride will precipitate from the solution after mixing. So what am I trying to get here? Q, and I'm comparing Q to K. Okay, and then I say, will it precipitate? So that means, is it saturated or not? If it's saturated, it will precipitate. If it's not, it won't. So I'll let you do that problem at home so that we could...
That's the one that we did in lab, like that, using the liters.
Okay, so yeah, so you guys should be familiar with it.
Yeah.
And that will lead us to selective precipitation. Okay. I was actually hoping to get through this whole chapter, this part of the chapter today. And this is about halfway. Okay. So, selective precipitation, what else we have? Complex ion equilibria, complex ion and solubility amphoteric, and the qual analysis. Okay. Okay. We are currently about 3 lectures behind, which is okay in the context of, that's because we have good questions and people are asking things and you're learning. Otherwise, there's no reason for me to be here if I'm just going to talk right off the board and not engage. So one of them is I think at the end of the semester, one lecture is just a review or something. That will clearly be a lecture. One of them is also on a different topic. I think I put in there radioactive ions or something like that, radioactivity or something. We will not do that. In fact, let me pull this up to make sure. Let's walk through together.
Radioactivity and kinetics decay?
Let me see. So I gotta remember what I put in here myself.
20.2.
102, I'm just gonna put it up on the board. Oh, it's already. Okay, so May 24th, review for final exam, that's clearly gonna be a lecture. That's the last day of lecture. May 22nd, radioactivity and kinetics of decay. We're not gonna touch that topic. That's number 20, that would be an extra topic that I was trying to get to last semester before the fires, which we would have, by the way. But in this class, we're not going to get there. So that saves us 2 lectures. On May 1st, which is today, we were supposed to do what? Have an exam. So that's 3 lectures.
Oh.
If I get rid of exam 3, which I clearly thought about prior to now. Otherwise, I wouldn't, be mentioning it now. I wanted to see how far we got. I was hoping we'd get further. We didn't. So what I think I'm going to do is I'm going to eliminate test 3. I'm going to add, so test 3 is just chapter 17. I'm going to add 1 or 2 questions on chapter 17 onto the final. And then I'm going to give you some kind of a homework that would be representative of what that test would be. And then I'll just apply points to that.
That'll be awesome.
So I'll probably give that on Thursday. I'll give some kind of a homework page, 2-page something that will be worth about 20 points. So you're not going to get the full amount of points now that we originally started with. But you'll have about a 20-point, I'll call it a homework / quiz, and then it will be due on Tuesday. So you have the weekend to do it. Okay? And that will be on chapter 17 because at that point we should finish chapter 17. So after the lecture, I'll give that to you, okay, to take home with you. On the final exam, I'll add a couple chapter 17 questions to it, and I'll probably move up the total points in that exam from 150 to somewhere around 200. Obviously, I haven't decided that yet, as opposed to having, so you're missing out on a whole 100 points on this exam.
I was gonna say
So I'll
that.
probably increase, you get maybe 20, 25 points out of the take home, and then maybe 25 to 50 points out of the final exam additionally, that will be part of chapter 17 that will account for most of that 100.
Oh, okay.
Okay, that's what I'm thinking of doing. How do you guys feel about that?
Yeah.
That's a lot of pressure on the final.
Yeah, or a grade stand.
A lot of pressure on the final, because then we don't know where we stand, like the final could just literally kill us.
Yeah. That's what I'm kind of worried about too. Because I did really well in the
But
first
he's-
exam. The second exam I did okay. Then I was hoping to rebound the third one.
Right.
Yeah, same.
But you still have that opportunity on the final, right?
Right.
Yeah, but in the
You
Because
final,
it's
have
2
less
questions
than
now being
You've
overweight.
lost 25 points in the total.
You're actually
grade.
having 2 questions
So if
being
you didn't do
overweighted
well
that is going to
in the
actually go
last
ahead and
exam,
account for
you
those
take your
points that
grade
you're
down.
missing out of the 100.
Because there's
Which is
the same
75
amount of
points.
points.
You're already getting 25 points.
Hold on, keep it down, keep it down. Hold on. Go
The
ahead.
questions for chapter 17, like multiple or like,
There'll be like problems like we had at the end of the
Like
test.
written.
Yes, they'll be solving like these. It'll be all chapter 17. So there are 3 parts of it, A, B, and C, I call them.
Yeah. I like that. And you got the 25 points already assured. That's your homework. Then the other 50 is in the homework 2 questions.
Well, the alternative here is I could just leave the final at 150 and just add a couple questions 17 to it. I don't have to increase, I was only gonna increase it so that you had those points
Yeah, I think
available.
it's better. Yeah, it's better.
I thought it was better to get those points available, but
Alright, I'm sold.
if you don't want those points available, I could just leave it at 150.
Now I'm sold.
It's nearly 100.
Effort.
You're getting back.
Test 3, instead of doing, the back questions, why isn't the homework just the back questions and then?
That is.
It is?
That's what it is gonna be. It'll be a homework that will have just solving problems,
Problem solving. Yeah.
problem solving.
Will there be any other like homework assignments for,
Oh, like
throughout,
quizzes or
for the rest of the semester, or just this one?
Just this one.
This was the only one I was suggesting. Are you suggesting that you guys would like more homework problems?
Yeah.
So, okay, so there's a difference between homework problems and assigning points to homework problems. Right,
Oh,
those
you
are
mean
two
like
different
exit
things.
tickets?
I could just give you homework problems, which you guys already have also in the Prof Pass.
Exit tickets.
Then it's a matter of should I assign points to those or not? So are you guys suggesting that you want points? Don't forget, now, keep this in mind. I curve everything, right? So getting more points does not mean you're gonna change where you are on a curve. Maybe that's lost there, that's a subtle concept there. In other words, if everybody gets hundreds on all these, I give a bunch of homework and you guys get another 500 points, everybody gets 100. That doesn't change where you're at on the curve relative to the exams. Do you see what I'm saying? Having more points for just to have more points isn't necessarily a benefit to anybody. So, right, if it's, I'm gonna give you some challenging problems for the homework ideally, and the same kind of stuff that I'd expect you to be able to solve on an exam.
Right.
Except for now, clearly you can collaborate and whatever else, and that's why I was only assigning a small amount of points to it, just to make sure that you did it, and then demonstrate that you understand that material. And then I'll have a couple extra problems on the final exam related to some of these topics.
Yeah, I like that.
That was the only thing I was thinking of doing, as opposed to having a whole nother 100-point exam where you now are being distinguished from each other, and we're wasting a lecture period. That's really where the key came from, right?
Right.
There's no real advantage by just having more points. I just want to point that out, because that might have been a subtle thing lost. Dieter?
I was just gonna ask if we can maybe still do, like, at least for the ones that wanted a third exam, because some of us, like, we've already started studying really hard because we thought that the test would be maybe like sometime next week, so like we've already started studying, and like I've spent a lot of time studying for this exam already.
But you're gonna need that for the final. That doesn't go away. You're not wasting your studying.
Go with this first off
You
first.
still need it for the final. You're gonna have a couple questions on the final.
You said that a couple questions will be written and
On
multiple
the
choice?
final, I don't know. I haven't decided that yet. I'll probably have a couple multiple choice and maybe one or two end of the chapter or end of the. So that you still need to know those things. And you'll still need to know it for the take-home thing, I think.
So the final, because you're removing one subject from it, the final is only going to be on 3 sections.
The final will be on all the sections that you would have been on plus 17.
But it won't have chapter 20.
Won't have chapter 20, no. Yeah. So the final will not have chapter 20 on it, obviously. But it will have 18 and 19,
That's good.
but it will now include 17.
Yeah, that's good.
Does that make sense?
But just to clarify, would the final have a good amount of 17 questions?
Well, the final is a time frame that I can't change, so you have 2 hours.
Okay.
So whatever I put in there has got to be within approximately 2 hours. No matter what. If I were to put in 8 chapters or 1 chapter, I gotta fit it in 2 hours. Right? So keep that in mind. I don't have a lot of flexibility there. Obviously, I could take you if somebody's coming into here and people are still working, and I've done this before and we'll probably do it for you guys. I could bring you into one of my labs where you guys can finish working on it and give you more time. But I still got to fit it into what I'm expecting to be a 2-hour final, right? Regardless. So I only have so many questions I could ask, and covers 18, 19, and whatever I'm putting in for 17, and 20 was, I think it was cut down, so it was only like 1 lecture of chapter 20. So that means whatever would have been chapter 20 would have been less than 18 and 19 already, and now that will be replaced with 17. Is all I'm saying.
Yeah.
Does it all make more sense? Okay, no, that's good. That's what I would assume most people would like it because not only are you prepared and you need to prepare still for this chapter, but you're just not worried about a third exam. I should point out in a 10-week quarter, you saw the transfer center was in here earlier. Most science classes in a 10-week quarter, they have 2 midterms and a final, and that's it. So if you're a UC other than Berkeley, which is kind of odd, I think they're on the semester, even though they were the first UC to go to the quarter, they're the only ones not on it. That's to kind of tell you something, but let's assume you're on a quarter or something like that. You only take 2 midterms and a final.
Yeah.
Right? We put in 3 here because it's a semester, but also to give you a chance to prepare separately for each one. If I'm taking out 20, I'm just replacing. 17 is more expensive than 20. But then again, I can only put so many questions in a 4 exam, so I'm not going to overload with 17. Anybody opposed to that idea? Peter, you sort of had a little opposition there. Are you still study all you want for? I mean,
They're gonna feel bad about it.
My friends in McKinney right now.
Oh, for
you would
real?
bid on that. Replacing 20 with a win rate.
Did you win any? Oh, he's not on the study.
It would have been on that.
1-1, pero 3-2.
Hold on, keep it down, because this could be an important comment. Let's hear what Peter says.
I feel like I'm the only one, so.
Well, but I want to make sure that you're clear, though. I'm taking out 20 and placing 17 in replace of it. You see, does that make sense?
Yeah.
It's not, you're getting 3 chapters either way on the final. The 3 chapters that you're now getting are different. 18 and 19 are the same. I'm now including 17 since we're not going to have time to do 20, which is the whole reason why I was able to do that.
Peter, are you worried about the time frame between now and then? Is that weird, like there's a lot of information?
No, I thought there was gonna be like 4 different chapters on the final.
No. 3.
I didn't want that. Okay, so.
The same 3 will be on the final either way. Now it's a different 3. 2 are the same, 1's different. Okay, so that's how we're going to do it. And I'll see you guys on Thursday.
Thank you, doctor.
Sure. Appreciate it.
A la Madrid.